Hello and welcome to the recitation for fluid mechanics for chapter 2. We're asked to develop an expression for the pressure variation in a liquid in which the specific weight increases with depth h as gamma equals kh plus gamma naught, where k is a constant and gamma naught is the specific weight at the free surface. So let's take a coordinate system as per figure 2.3 on page 44, where the free surface is at z0, where gamma is equal to gamma naught, and h is a height as indicated on the diagram, and z is measured from the bottom. And let's say at some h or some z, gamma is what the specific weight would be. We know that the pressure varies hydrostatically for a static fluid. We have dP over dz equals negative gamma. And from the diagram, h is nothing but total z naught minus some z. So at h equals 0, that means z naught is equal to z, that means at the free surface, we know that gamma is equal to some gamma naught. And also if we take the derivative of this equation, we get dh equals negative dz. The reason z naught gets cancelled is can be treated as a constant at some height. So we have dz is negative dh. And also we have dp is equal to gamma dh, because I can replace dz with negative dh. Now if I want to find pressure variation, I can take the pressure at the free surface to the pressure at some location, and as h varies from 0 to h, gamma dh, and I can substitute here for gamma as kh times gamma naught plus gamma naught. So with that I can do a simple definite integral, and I can evaluate p to be kh square over 2 plus gamma naught times h. In this problem, Pikes Peak near Denver, Colorado has an elevation of 14,110 feet. In part A, you are asked to determine pressure at this elevation based on equation 2.12. And in part B, if the air is assumed to have a constant specific weight of the value shown, what would be the pressure at this altitude? And finally, if the air is assumed to have a constant temperature of 59 Fahrenheit, what would be the pressure at this elevation? And for all three conditions or cases, we are asked to assume standard atmospheric conditions at the sea level. That means we could use table 2.1. So the relation between pressure as it varies with altitude is shown here. PA, TA, and beta and R values can be obtained from pages 49 and 50 respectively. So we can substitute those numbers in couple of steps here. So for PA, TA, and then beta value from page 50, and then we are given the altitude. And then C is nothing but G over R beta. So we can substitute G, R, and beta in English units, and then we can get P to be 1237 pounds per square feet in absolute scale. And then in part B, if we assume that gamma is constant, it simplifies to simple hydrostatic pressure equation where P is equal to PA minus gamma h. We know these values, so it is 1037 pounds per square feet. And then if we use equation 2.10 for a constant temperature, we can again obtain the pressure as 1271 pound per square feet. So you can see at this altitude, assuming gamma equals constant would lead to a slight error in the way the pressure is computed, but it's not significant. A Borden pressure gauge attached to the outside of a tank containing air reads 77 psi when the local atmospheric pressure is 760 mm of mercury. what will be the gauge reading if the atmospheric pressure increases to 773 mm of mercury. So we know that the gauge pressure is nothing but the absolute pressure minus the atmospheric pressure. Let P absolute of air in the tank be constant. So initially P gauge is 77 psi and P atmospheric pressure is 760 mm of mercury. That means the height of mercury is given. Here we are interested in the final gauge pressure when it is as shown, and then the atmospheric pressure is 773 mm of mercury. So we know that the absolute pressures in both cases have to be the same. So we could use that fact and then solve for the gauge pressure at 2, where you write the gauge pressure at 1, which is 77 psi, plus gamma times H1 will give us the atmospheric pressure in pounds per square feet, and we can convert it to pounds per square inch with the corresponding unit conversions. And the reason you have to do gamma H is it is given as height of the mercury, so you need to multiply that with gamma, which is the specific weight of mercury, to determine the final gauge pressure, which is 76.8 pounds per square inch. A U-tube manometer is connected to a closed tank containing air and water as shown. So this is your U-tube manometer, this is your tank. At the closed end of the manometer, the air pressure is 16 psi A. You're asked to determine, which is shown here, you're asked to determine the reading on the pressure gauge for a differential reading of 4 feet on the manometer, which is this reading of 4 feet. So you're asked to find the pressure gauge reading here. You're asked to express your answer in psi gauge. You're asked to also assume standard atmospheric pressure and neglect the weight of the air columns in the manometer. And this is typically the case because the density of air is so low compared to water. Air pressure is 16 psi. Let's take that as P, which is for this case. So P plus gamma fluid plus times the height of the fluid. If I start here, I go down the tube, and then since it is the same fluid here, I can march along, plus gamma water times H water, which is equal to the gauge pressure here. So the P gauge is P plus gamma of the fluid, which is 4 feet, plus gamma of water, which is 2 feet. And then we know that P gauge is P absolute minus P atmospheric. Since we are asked to assume atmospheric pressure, standard atmospheric pressure, we would take that to be 14.7 psi. So we get P to be 1.3 psi. And then P gauge is equal to 1.3 psi plus you substitute all the corresponding values for the specific weight for the two fluids, gauge fluid and the water, and the corresponding heights, and then make sure you convert them to the inches if everything is to be in pounds per square inch. So your final answer is 4.67 pounds per square inch. The reason we didn't have to consider this particular height of air because they asked us to ignore the weight of the air column in the manometer. In this problem, we have an inclined tube manometer where the pressure in pipe A is 0.6 psi and the fluid in both pipes A and B is water. And the gauge fluid in the manometer has a specific gravity of 2.6. Remember, specific gravity is defined as density of the fluid over density of the water. You're asked to find the pressure in pipe B corresponding to this differential reading. So again, in these problems, you start off with a certain location in your system and then go along until you get to the end of the structure. So in this case, let's start with PA, which is pressure in this container. Then I move along the tube and come down at a location where the height of the water is 3 inches. So you can see here plus gamma water times 3 inches. The reason I'm adding is whenever I go down the tube, the pressure increases, so I need to add it. And then since there is a different fluid here, and also the fact that the height of the fluid is what we are interested in, you take the specific weight of water times the 2.6, which is the specific gravity, will give us the specific weight of the fluid contained in this inclined portion. And remember, we always consider the heights, not this length. Times sine of the 30 degrees, which is the angle given, will give us the height from there to the height from here. So from here to here is 8 inches times sine 30. And then we stop here, and then you can see that again we are interested in the height of water. As you go up, you subtract the pressure, so minus gamma of water times 3 inches. Since we have a plus gamma 3 inches minus gamma 3 inches for water, those two cancel, and then that is what the final pressure will be felt at PB. So solve for PB here, you get 0.224 psi. Here we are given a mercury manometer, and it indicates a differential reading of 0.3 meters when the pressure in pipe A is 30 mm mercury vacuum. You are asked to determine the pressure in pipe B. Again, you would start with some location. It doesn't matter whether you start with A or B, you just follow along the tube until you get to the last point. So let's start with A. So pressure at A, and then I can move along the tube, and then I go down the tube until I hit this height 0.15 meters where I still have water in that column. So I add the pressure because I'm going down the tube. And then there is a different fluid here, which is mercury. So I continue from this location to here, and the height there is 0.3 meters. So multiply that with the specific gravity, add it. So that gives you the pressure in this column. Then I can move down this particular location because the pressure remains the same if it is the same fluid and the fluid is at rest and we are in the same horizontal plane. Then I can move up to this location where the height is 0.45, and then I put a negative sign because I'm going up the tube. You don't have to go up here because since B is in the same location as this point, I can say the total pressure then would be equal to PB. Make sure you convert the height of the mercury into gamma, and since it is vacuum, you put a negative sign. So finally you get PB to be 33.35 kilopascals. In this problem, a structure is attached to the ocean floor as shown. A 2-meter diameter hatch, which is this hatch shown here, is located in an inclined wall and hinged at one edge. This is the edge where it is hinged. You're asked to determine the minimum air pressure P1 within the container to open the hatch. You're asked to neglect the weight of the hatch and the friction in the hinge. So for these problems, it is always important that you recognize the free surface and measure any distances from the free surface. So let's first find the resultant hydrostatic force, which is gamma times height of the centroid times the area. The height of the centroid is again measured from the top of the free surface, which is 10 meters plus half times 2 meters times sine 30, which is 10 and a half, which is somewhere here. So Fr then becomes 3.3 10 to the 5 newtons. And then the resultant hydrostatic force acts at some location, which is YR, which is nothing but IXC over YC times A plus YC, where Y is measured along the plate. So YC is 10 meters over sine 30 plus 1 meter, which is the radius of the hatch. Since it is 2 meter diameter, the radius will be 1 meter. So YC measured from the sea surface all the way on to the hatch center is 21 meters. And remember, the hydrostatic pressure, the resultant hydrostatic pressure always acts at a location called YC. And then YR can then be computed, and this you can look up the figure to get the IXC values. And then I get the YR. Then, since I'm interested in finding the pressure, I could draw a free body diagram and then convert that pressure into a force by multiplying by the area. And if I take the hinge as Hx and Hy as the two forces, resultant forces there for the hinge, and then I take for equilibrium condition, I take the moments about H, I get Fr times the moment arm from that location H times P1 times the area, and then the location of the moment arm in this case is 1 meter. So I can get P1 as 107 kilopascals. In this problem, a 3 meter wide, 8 meter high rectangular gate is located at the end of a rectangular passage that is connected to a large open tank with water as shown. So this is the large tank where this is the gate which is hinged at this location at the bottom. The gate is hinged at the bottom and held closed by a horizontal force as indicated, and it is acting upon at the center of the gate. The maximum value of H is determined to be 3500 kilonewtons. You're asked to find the maximum water depth H above the center of the gate that can exist without the gate opening. Is the answer same if the gate is hinged at the top? And you're asked to explain your answer. So the first thing is indicate your heights always from the centroid. Take your coordinate system x and y as shown, and then indicate all the resultant force and the resultant YR and so on. So resultant hydrostatic force is a simple calculation here which we would do in a minute, but the resultant force always acts at some location YR. The horizontal force acting on the gate, if we draw a free body diagram, is already given as 3500 kilonewtons, and YC for this case is nothing but the height H. And H1, if you do little bit of algebra for this problem, you get H plus 4 minus YR. And then if I take the moments about H, I get Fr times the distance times equals Fh times 4 meters. And then at this point I have to find YR. Again, for a planar rectangular gate, IXC could be determined from the figure. 1 over 12 B times A cube. So you have the gate here which is 3 meters wide and 8 meters high. So B is your 3 meters wide, A is your 8 meters high. Cube divided by H times 3 times height, that is the area of a rectangle, plus H. And then I have Fr, the resultant hydrostatic force, as gamma height of the centroid times A. So here for our problem, what we ended up is an equation where h is the only unknown. So we have one equation, one unknown, and the height is 16.2 meters. This is when the gate is hinged at the bottom. We can do a similar analysis when we hinge the gate at the top, and you will find that the height determined is 13.5 meters, which makes sense that if we hinge the gate at the bottom, the amount of water that could be held increases rather than holding the hinge at the top of the structure as shown in this diagram. And you can see here the height is 13.5 meters when the hinge is at the top, and it is more when it is hinged at the bottom. So more water can be held when the gate is hinged at the bottom. The 18 feet long gate, that means if you go into the screen here, the width is into the board, is a quarter circle and is hinged at H. You're asked to determine the horizontal force P required to hold the gate in place. You're asked to neglect the friction at the hinge and the weight of the gate. So here we have a curved surface. So in this problem, we could take this problem as if we would be dealing with two planar surfaces. The way you do that is take a section of the fluid from the container such that we have two planar surfaces, this one, and the resultant hydrostatic forces can be written as Fv and Fh, which are the horizontal and the vertical components. If I draw the free body diagram for this fluid column, I have the weight of the fluid, I have the resultant hydrostatic force components Fh and Fv, and then the planar component force F1 as shown here. For equilibrium, if I sum the forces in the x direction, F1 is nothing but Fh, which is equal to gamma of the water, height of the centroid, times the area. And here the area of the planar surface is the height here, which is 6 feet, times the length of the gate into the screen, which is 18 feet. And that gives us a force. And then we can do a sigma y, Fy equals 0, where the vertical force should be equal to the weight of the fluid column. In this case, we can write weight as fluid volume times gamma of water, and fluid column, since fluid volume is nothing but the area times the length of the gate. In this case, since it is a quarter circle, we have pi over 4 times r square, which is 6 feet, times 62.4 pound per cubic feet, which is gamma for water. So you can find the vertical force. And then we can draw a free body diagram for the gate. Remember, we are trying to find the required horizontal force P. If we do that, we can then take moments about O, which is the hinge here, and then the moment about the hinge is the sum of the moments. It should be equal to 0 for equilibrium. So P times 6, which is the moment arm, equals Fh times 2, which is the length of the moment arm, and then Fv times the moment arm, which you can find from page 62. You can then find the horizontal force P required to hold the gate in place. A homogeneous timber AB of certain cross section is given. You're asked to determine the specific weight of timber and the tension in the rope. So in this problem, since water is on both sides of this timber, the hydrostatic force, the resultant hydrostatic force, is nothing but the buoyancy force, which is shown here. So the net effect is the buoyancy force. You draw the free body diagram for the timber. You can write the weight of the timber as gamma of the timber times the volume of the timber. The specific weight of the timber is something which we don't know. Keep that in variable form. We know the volume of the timber, which is nothing but the cross-sectional area times 0.15 times 0.35 times the length of the timber, which is 10 meters. And then the buoyancy force should be equal to the specific weight of the water times the submerged volume of the timber. So here when we say submerged, the length is 8 meters and the cross-sectional area remains the same. So you get 0.42 gamma of water. And then for equilibrium, moment about A should be equal to 0. We are not given an inclination for this timber, but we could take some angle and you would see that that eventually cancels out when I want to find the moment arm length, and I know gamma for water. So that gives me gamma for timber, which is 6.27 kilonewton per cubic meter. And then I also need to find the tension in the rope, which is here. So whenever you want to find the force here which is involved, you draw a free body diagram, which we have already done. And then since this force is in the y direction, sigma Fy is equal to 0. So tension plus weight of the timber should be equal to the buoyancy force, which is the net force acting upward. So T equals Fb minus the weight of the timber, which gives us 824.25 newtons.